So from this lecture, we are going to start a new module, and this is a module on RF power amplifiers. So these power amplifiers basically occur at two locations. One is in the audio system, immediately before the speaker, and second is here in RF domain, immediately before the antenna. And both are responsible for giving more power to speaker and the antenna. So we have already seen that immediately before the antenna, what we encounter is an amplifier, and this will be called as RF power amplifier. And it is this power amplifier which delivers output power PO to the antenna, and then antenna converts this power into wave, electromagnetic wave, which is then radiated. So what is the distance up to which this signal can be received is decided by this power which is fed to the antenna. And this power is produced by this amplifier, which takes certain amount of input power, and then it basically draws more power from DC supply and converts this DC power into RF power. So the distance of reception or the distance of transmission by this transmitter is directly decided by this power amplifier. So if power amplifier is able to give more power to antenna, you will be able to receive the signal at a larger distance. So this is a very important element in the transmitter path. And here there are various characteristic parameters about this amplifier that usually we encounter in the data sheet. So we will mention some of them and then talk about some of those parameters in more detail. And then when we start studying various power amplifier circuits, we will try to derive some of those parameters and then try to see that which of the power amplifier circuit is better than the other one. And here we will be defining power gain. PO by PI. So output power from the amplifier and the input RF power to the amplifier. So first parameter that we will list and talk about is efficiency. So efficiency here is defined in two different ways. So first is drain efficiency, designated as eta D, and this eta D is equal to RF power to the load divided by DC power from the DC supply. So this is one way in which efficiency is defined. Second way of defining the efficiency is called power added efficiency. Or in short, PAE. And this eta PAE is defined in this way. So here, in the previous efficiency definition, we included RF power to the load in the numerator. But here you note that whatever power is delivered to this load, which is going to be an antenna, this power is contributed or it comes from two different sources. One is this input power itself, and second is power drawn from the DC supply. So whatever we see here, it has two components, from DC and from the input power. So actually the amplifier's contribution is the contribution in terms of the DC power that it converts into RF output power or power to the load. And PI is anyway the input to it, so it is not something that it adds, but it is being provided. So then this second definition of efficiency says that you subtract this input power because this was not the creation of the amplifier. So what it says is that find out the RF power to the load, from it subtract the RF input power, that is PI, and then of course divided by DC power. So this will give the more clear idea of how much amplifier is creating the RF power. So here this can be manipulated. So what we see here is we have PL by PDC. So this becomes then 1 minus PI by PO. And this then it can be written as this factor is drain efficiency, and factor inside this bracket, this factor is 1 by G. So here we can see that this is a composite efficiency. That means it depends upon two parameters, drain efficiency and the gain. And what is desirable? What we want is G to be high and eta D also to be high. So we want eta D to be high. That means good amount of RF power to the load, and compared with the DC power. Ideally, we would like that RF power is equal to the DC power drawn from the DC supply. So we want both of these to be high, and this will then imply eta PAE also to be high. So here, this power added efficiency is also called a figure of merit. So this tells that which of the two amplifiers are going to be better, because it incorporates two parameters which are very important for amplifier. Now here, why we have listed efficiency as the first parameter for the power amplifier? Because here you can see that this amplifier is going to deal with large power. So it will be generating large amount of output power, and obviously it will be drawing large amount of power from DC. So any system where large amount of power is handled, efficiency becomes important, because we know that efficiency is going to have impact on various aspect of the this power amplifier or the overall transceiver. So if we have, say, for example, low efficiency, So what are the disadvantages that we will have? So the first disadvantage that we will have is that lot of heat will be generated. So poor or low efficiency means not the complete or not the major portion of the DC power is getting converted into RF power. So if not the entire DC or major portion is getting converted into output power, then what is happening is a lot of power will get dissipated in the form of heat in the amplifier itself. So if we have an amplifier which has poor efficiency or low efficiency, then it will generate a lot of heat, and then this will require a heat dissipation system. So this system will be required so that the heat getting generated in the amplifier can be dissipated. And then issue with this is that of course this will require additional cost, and it will make system bulkier. So if you want to design a compact system, then it will be a challenge under this condition. So this is one disadvantage. Second is wherever we have a lot of power being handled and a lot of heat getting generated, it reduces the life of the system. That means system will tend to break down very frequently. So reliability is going to be low. So this is another undesired consequence of low efficiency. Then the third undesired consequence is, if suppose this DC supply that we have here is from a battery, that means this entire system is handheld. In that case, a lot of power will be drawn from the battery, and the battery will discharge very frequently. So you need to charge it very often. So low battery life. So this is undesirable. However, if suppose the system is being operated by connecting it to the main supply, that means it is not battery operated. In that case, disadvantage will be that it will be drawing a lot of power, but giving very less output power in the form of RF power. So for any given system, this will lead to high electricity bill. So operational cost is going to be high. This is another undesired consequence of this. And fifth one, I have already pointed out, because it has low efficiency, that means it will be generating less power for any given input DC power. That means antenna will be getting less power, and transmitted signal is going to be weaker. That means distance of reception or the distance of communication is going to be low. So and if you want to cover certain area, then in that case, you will have to pump more power. That means additional cost and additional heat generation. So you can see that there are many undesired and very powerful undesired consequences of low efficiency. So that is why for the power amplifier, or in fact any system which handles a lot of power, we always try to see that the efficiency is very high. And that is why I have mentioned this efficiency as the first parameter that we are going to study for various power amplifier circuits. Then the second characteristic parameters is well known, 1 dB compression point. So this point becomes very important. Unlike low noise amplifier, for the low noise amplifier, this input power is already very small. but here input power is going to be sufficiently large and output power is going to be still larger. So it's very probable that we will be operating or we will reach close to the 1 dB compression point. So this P1 dB is mostly used for power amplifiers. Similarly, then IIP3 point. So this is also very important for power amplifiers compared with the low noise amplifier. So we have already studied these two parameters. Then there's one more parameters. So in fact, there are many parameters. And then we have stability. Stability is important, in fact, for every amplifier because it tends to become oscillator. That means it will start giving very high gain for certain frequency and no gain for rest of other. So it should not oscillate. And then, of course, this gain and bandwidth. So these are the usual parameters for every amplifier that we talk about. And input and output impedances. And there's one more parameter which we will emphasize for power amplifier is actually stress, the electrical stress on the transistor. So in this case, we are going to use MOS to study all the circuits. So we will be talking about the stress, electrical stress on MOS. So if you see the power amplifier circuit, circuit is typically going to be of this form. So here we have RL. Actually, this RL means the antenna in real life. And then we have DC supply here, and we have RF choke. That means very large inductor. And then we will be having here input, the RF input, which will be, of course, time dependent. And then there will be certain DC voltage, which will be used to bias the gate. That means transistor remains in the conduction mode for suitable duration of the input cycle. And then we have here a network of L and C. And the purpose of this is going to be, you will see, to filter out undesired harmonics. So here you can see that when this device operates, it experiences certain drain to source voltage. So VD source is anyway ground. So there will always be certain drain voltage and it will always be experiencing a drain current. So what do we mean by electrical stress on MOS is the maximum value of this drain voltage. Because we know that any device will be able to tolerate only a certain amount of voltage across it. Similarly, any MOS will also be able to tolerate a certain maximum drain current through it. So in real life, every MOS will have upper limit on these two parameters. And because this power amplifier generates a lot of power, that means it will always be having a large voltage and large current. So there is always possibility that these two parameters might reach or might exceed also the limit of the MOS that we are using for designing power amplifier. So this is another parameter, and this is mathematically conveyed by defining a ratio that is called normalized power output capability. And this is defined as Pn is equal to actual RF power to the load divided by maximum of drain voltage into maximum of drain current that it experiences. And fortunately, we will see that maximum of these two, they do not occur simultaneously. So they will attain their peaks at different moment. So it will be experiencing maximum voltage at one moment and maximum current at another moment. So we will be studying these parameters also for the various MOS based power amplifiers. And here you can see that in this list, we did not talk about the noise factor or noise figure, because in this case, this input voltage is going to be itself quite large, because this is coming from the, this is in the transmitter path. So the signal generated itself will be amplified and then fed to the power amplifier. So it will be quite large and much large compared with the noise. So we never talk about the noise factor or noise figure of power amplifier. Now we are going to classify these power amplifiers into various subclasses. But let me emphasize that this classification is not in terms of common source, common drain, common gate, because here you can see that this power amplifier is always common source, because only in the common source you can have large VD as well as large ID. So this is possible only in common source. That is why all the power amplifiers that we will consider will be fundamentally a common source configuration. But this classification is with respect to the first parameter that we talked about, that is efficiency. So it is the efficiency which leads to various classification. And in fact, that classification will manifest, of course, in form of various circuits and the various waveform for the drain voltage and the drain current that we just listed. So broadly, there are two classes. First is called linear class, linear power amplifiers, and second is switch-based power amplifiers. So let me again emphasize that all these classification is carried out, or all these circuits, they have been devised primarily to attain high efficiency, and of course to ensure that gain is high and stress is also tolerable, in addition to, of course, maintaining desirable value for the remaining parameters. So under the first class, that means linear class, we have four different types of power amplifier. So they are class A, class AB, class B, and class C power amplifiers. These are the four classes. And by looking at circuit, it will not be possible to say which class the given power amplifier falls into. For finding out which class it belongs to, we will have to see the waveform for the output drain voltage and the output drain current. So we'll talk about those things shortly. And Under the switch base category, we have class D, class E, and sometimes this class F is also put under this category, but some of the authors, they will put into the first category also. And there are a few more classes also. But in this course, in this module for the power amplifier, we will study all of these 7 classes of power amplifiers. And we will basically try to find out the efficiency, drain efficiency for each of these cases, and then try to see that which one is better. But we will see that some of them will turn out to be equivalent in terms of efficiency. So then question arises if, for example, class D and class E, they both have 100% drain efficiency. So then question arises that then why we invented class E and so on and so forth. So answer lies that although 2 power amplifiers might have same drain efficiency, they might have different gain, and they might have different stress on the device that is being used. So, and the ease of designing is also another factor. So now we are going to see in the detail what is the how we define class A, class B, and C, and so on and so forth. So first we will talk about the linear class of power amplifiers. So here all these classes they are based on what is called conduction angle. So conduction angle is used to classify the linear power amplifiers. Now, let us see that what do we mean by conduction angle. So here I had already pointed out that all the power amplifiers, at least of linear class, they will have this general structure or topology. So we'll see that all the power amplifiers A, B, C, and AB, they actually will look like this. So here we have RFC, which was pointed out is large inductor. So this large inductor ensures that there is only DC current flowing through this. No time varying current will pass through this path. And at the gate, as was pointed out, there will be gate to source DC voltage, and then there will be time varying RF or the AC signal. So here we will be taking input as A cos omega t. And there will be total drain current, which we will see is going to be sum of DC plus RF, or in short AC. So that means all the RF or AC current will actually be flowing like this. So we are using capital letters for symbol and subscript to designate DC, like here. We are using small letters for the symbol and capital for the subscript to designate total quantity, like this, which will have both DC and AC part. And we are going to use small letters for both symbol and subscript to designate AC quantity. So this is the convention that we are going to follow. So that is what we have done here for voltages also. So now we are going to see that what do we mean by conduction angle, and then how it leads to those four classes of the amplifier for the same circuit. So we will start the story from the input side, because here we see that this is the independent variable or the input, and it determines this drain current, which is the output quantity. So this is output quantity and this is total input. So we will first talk about the input. So what we have here is total gate to source voltage is DC plus AC. So now if you see this thing graphically, so what we have here is so this is our total gate to source voltage. So what we have here is DC. So DC is let us say here. So our time varying AC is varying about this DC line. So the actual waveform is going to be like this. Here. So here we have amplitude A like this. And this is the zero line. And we have one period of this much duration, or in terms of angle, this is 2 pi. So this is one cycle. And this waveform is Vi. So for this MOS, we know that the drain current is given by this equation. Total drain current is equal to 1 by 2 mu n COX W by L total VGS minus VTH whole square. This is the equation valid in saturation. So here we see that only when this quantity VGS minus VTH is greater than 0, only then it will imply that non-zero drain current exists. And if this VGS minus VTH is less than equal to 0, that will imply the drain current to be 0. So this is for the real MOS. And we are talking about real MOS because we have this threshold voltage. Otherwise, for ideal, and this is the MOS that we will consider, equation will be something like this. 1 by 2 mu n COX W by L, simply VGS, total gate to source voltage. So for ideal case, this threshold voltage is assumed to be 0. And this is what we will take up for all the circuit that we will consider. Right. So we are going to carry out analysis for ideal case. So now you can see that what we are giving at the gate is a voltage, total voltage containing DC and AC component. So now here also whenever VGS is less than 0, this will imply drain current to be 0, negative or equal to 0. Only for the positive gate to source voltage, there will be finite non-zero drain current, total drain current. Now, I pointed out that in general, we will have two components for the drain current here. You can see a DC component and the AC component. So let us briefly see that what will be those two components before we proceed to talk about the various classes. So this equation says that you just substitute the gate to source voltage and find out the total drain current. So total drain current, we will be calling this factor as K. So this total gate to source voltage is gate to source DC plus the RF or time varying part or AC. So here this will simplify to VGS square plus VI square plus 2 VGS VI. And this, now here if we have a small input, so if VI is small, VI square is going to be even smaller, and this can be neglected. So this will lead to total drain current as K into VGS square plus 2K VGS into VI. So now here you can see that this quantity is DC independent of time because K is constant and GS is also constant. But here you can see that this part is constant and this is time varying. So this is AC part. So this leads to a DC current which will be flowing through RF, RFC, and then we have time varying current which will be flowing through the load network. This much portion will be called as load network. So everything on this right hand side will be called as load network. Right. So additionally, we see that this ID, the time varying or the AC part, is equal to 2K VGS into VI, and in fact, it will turn out to be GM into VI ID. So here you can see that if this is cosine, this is also going to be cosine. And the relation here you can see is Y is equal to MX. So it has a linear relation between input and output. And this linearity is valid only if VI is very small. So such type of amplifiers, they are also called small signal amplifier. Unfortunately, these power amplifiers that we are going to talk about, they are not going to be small signal because this is not going to be small. But yet, we are going to assume that this is small signal so that we are able to derive the expression for the drain efficiency. Of course, that is going to be approximate because we are violating this fact. So there are two simplifying assumptions that we are going to assume. One is that VTH is equal to 0, and second is VI small. So these two things are going to be assumed for the linear class of power amplifier. And now you can see that why these classes are called linear, because of this kind of output relation that we are getting with respect to input. Okay. So now we know that what are the various components of the total drain current. We can now proceed to define the conduction angle and then arrive at the various classes of the power amplifiers. So for so what we have seen here is that most important thing here for amplifier is that gate to source voltage should be greater than 0. VGS greater than 0 implies non-zero drain current, and then only of course you can get voltage. So as long as this condition is valid, we will say that MOS conducts. And portion of the cycle, portion of one period T, for which MOS conducts, is used to define the various classes or the conduction angle. This will also lead to various classes, and this will also lead to conduction angle. So I will first read the conduction angle definition. Say, for example, we have this kind of scenario. This is total gate to source voltage. This is zero line. And then what we have is, this is VGS, and my input is going to be about this. So this much portion is the amplitude of the input. So here we see that VGS is less than the amplitude. And we find that for this much portion, so for this portion of the cycle of the input, the VGS, net gate to source voltage, VGS is negative for this portion. So this implies ID is going to be 0 for this portion. That means only for this much portion, tau, ID is greater than 0. So we say that MOS conducts for tau duration. Now conduction angle theta is defined as 2 pi into tau divided by total time period. So its time period is going to be this much. So duration over which gate to source voltage is greater than 0 will lead to the tau or the conduction angle. Now, based on this conduction angle, there are going to be 4 classes of the power amplifier. So we will first tabulate those classes. So first class is called class A. For this case, this conduction duration is equal to the complete cycle. And since tau is equal to T, so you can see that conduction angle theta is equal to 2 pi. Conduction duration is tau, conduction angle is theta. Now, there is a third class, class B, for which the conduction angle is, conduction duration is going to be half of the cycle. And for this case, the conduction angle is going to be pi. And there's a scenario when this MOS conducts for duration more than half of the cycle but less than the complete cycle. So for this case, the conduction angle will turn out to be anywhere between pi and 2 pi. And this class is, since it is conduction angle is between that of class B and class A, so this is why this is called class AB. So here for class A and class B, conduction angle is fixed, equal to pi for B, 2 pi for class A. However, for class B, it could be anywhere between pi and 2 pi. So there is a range of conduction angle for class AB, but fixed conduction angle for class A and B. So now here you can see that there is now the fourth possibility is that the conduction angle is less than T by 2, but greater than 0. So this will imply the conduction angle is greater than 0, but less than pi. And this is the last class, and it is called class C. So these are the four classes of the power amplifier, linear class of power amplifiers. So one question will arise that why we have these four classes, why we keep on decreasing the conduction angle starting from class A and finally to class C. What do we achieve, and is there any price that we pay? So answer is that when we decrease the conduction angle, this we will see implies increase in the drain efficiency, and this is desirable. So this is desirable, but unfortunately, the same decrease in the conduction angle also leads to reduction of power to the load. And this is obviously undesirable. So there are two consequences of decreasing the conduction angle, increase efficiency, decrease power to the load. And this, keep in mind, power to the load is important parameter because this is going to determine the reception. So once this is decrease, reception also decrease. So this is also undesirable. So based upon the application, user will have to choose which of the four categories he wants. Now we can see this thing graphically also for the various classes, for class A, B, and C. So for class A, what is going to be the waveform? So we have already seen this. So this is my DC gate to source, and DC gate to source has to be greater than the amplitude of the input. So that the net voltage is always positive. So this is my VI. So for this case, VGS is always going to be 0 because the DC gate to source is greater than 0. And this will then imply that we have this kind of total drain current. So there will be a DC drain current, which we have already derived, and this will be K into VGS square. So this is going to be the expression for this. And on this, we will be getting our input drain current. So here you can see that ID is always greater than 0. That means non-zero. So that means conduction duration tau is equal to T. That means for entire cycle, conduction is taking place, and conduction angle theta is going to be 2 pi. That means for the entire cycle of the input, we are getting non-zero drain current. This is the meaning of class A. Now for class B, what happens is that we make this VGS equal to 0. So for class B, we make VGS equal to 0. So now let us see what will happen. So this is total gate to source voltage. Now VGS is equal to 0. That means now my input is going to oscillate about the 0 line. So this is VI. So now the total VGS is simply going to be equal to VI. So in this case, we can see that VGS is greater than 0 for tau is equal to T by 2. That means if you see the drain current, then drain current is still going to be 0 for this portion. Sorry, I made a mistake. This current waveform will be in phase with the input. So the current waveform is going to be like this. Here. So we see that this tau is equal to T by 2. That means theta is going to be equal to pi. And ID is 0 for the remaining half of the cycle. So this is for class B case. Now for class AB, what we do is that we now take this VGS to be less than this case of the class A, but more than the class B case. That means we take VGS now to be somewhere between 0 and the amplitude of the input signal. So in this case, what will happen? If you see the total gate to source voltage waveform, this is total gate to source. Now my VGS is positive, of course, but less than the amplitude of the signal. Here. So we can see that my amplitude is this much. This is the amplitude. And this is VGS, this is 0 line. And this waveform is the time varying input waveform. So in this case, we can see that the wave input is negative for this portion. So here VGS is greater than 0. So this will imply ID 0. However, for this portion, VGS is greater than 0. This implies ID will be non-zero. But now you can see that this is the duration of the one cycle. This is T, and it is going to conduct for this much duration, tau, and tau is greater than T by 2, but less than T. And in this case, then we can see the drain current waveform. So since there is some finite gate to source voltage, so obviously there will be some gate to source, drain current will also be there, determined by this. So IDC is going to be there, non-zero IDC. And on this IDC, our drain current is going to oscillate. In fact, what I have shown here is wrong. Like this. So this portion will not be there. This is total drain current. And this much is one complete cycle, and conduction is over this portion, which is somewhere between T and T by 2. So theta is going to be somewhere between pi and 2 pi. Now for class C, what we do is we further reduce the gate to source voltage. Up till now, we have been taking gate to source voltage between 0 and more than the amplitude of the signal. So in this range, we have been varying for these three classes. Now we can make gate to source voltage negative. For class C, gate to source voltage is taking negative. So now you can see that the total gate to source voltage is VGS plus Vi. So this is now going to be less than amplitude of the input signal Vi. So here we will have this scenario. And gate to source is negative now. But my input is going to oscillate about this line. So here we find that this is non-zero for duration t, tau, which is smaller than the half of the cycle. This is complete, and this tau is going to be less than t by 2 but greater than 0. That implies theta is now going to be greater than 0 but less than pi. And in this case, you can see the current waveform. So it will be non-zero only for a small duration, for this tau duration. And it will be 0 for majority of the portion. So here also we will see that there will be DC current, because you can see that DC is basically the DC of this waveform. This is periodic, and there will be certain DC current flowing through the MOS. And so these are the four classes for the linear class of power amplifiers. In the switch-based power amplifier, what we do is we make the power MOS operate as a switch. So the circuit in general will be like this. So here we have a switch for the MOS. And we will again have a network of L and C to filter out any distortion. So we know that if switch has a voltage PSW across it, and if current is ISW through it, then we know that when switch is on, in that case VSW is going to be 0. However, ISW is not going to be 0. However, when switch is off, in that case, V switch is going to be non-zero, but switch current is going to be 0. So what we see is that the product of these two, product of V switch and I switch, is always going to be 0. Of course, this is for the ideal switch. So ideal switch have this behavior. So now if you calculate the average power consumed, then it will turn out to be equal to 1 by T integral from 0 to T V switch into I switch dt. And this quantity will turn out to be 0. So this is the basic idea of why we go for the switch. That means the ideal switch never consumes any power. And in fact, if you go to these linear classes and try to see that why we kept on reducing this conduction angle, then you can see that the basic idea was to keep this current 0 for more and more duration. So when the current is 0, whatever may be drain voltage for this portion across the MOS, the product of VD and ID is going to be 0. That means no power consumed by the MOS for this duration for which it is turned off. So in this way, we try to reduce the power consumed inside the MOS and hence increase the efficiency. So whether we talk about the linear class or whether we talk about the switch mode of the power amplifiers, in the both the cases, the essential idea is to keep this product as low as possible. For MOS, for switch base, this becomes always 0 for ideal scenario. For linear case, we try to increase it when we move from class A to AB to B and finally to C. So that way we try to increase the efficiency. But we will see that for linear classes, there is a price to pay in terms of reduced power delivery to the load.